Oh hey! I didn't see you there. I was just writing out this question for my induction. So to do this question, we're going to use the same kind of general steps of induction that we used in the previous induction question. And these steps were, we can only look at the black writing, that we show that it's true for the base case, we assume that it's true for the general term n equals k, and using that assumption it will prove that it's true for the following integer where n equals k plus 1. So for here, we're proving it's true for positive integers n. This means that our first case is going to be n equals 1. So we're going to show that it's true for n equals 1. We'll then assume that if it is true for this term n equals k, then it must be true for the following term n equals k plus 1. So if it's true for 1, then it must be true for 2. And if it's true for true, then it must be true for 3. And so on and so forth, to prove that it's true for all positive integers, which is what this little symbol means. But first, I think it's important to think about what this statement actually means. It's not too hard, it's really just substituting into an expression, but I think it's worth it nonetheless. So we're going to rub out, I think I'll keep the blue because that's telling us what our statement is. We'll rub out all this. Okay, so we need to show that for the base case n equals 1, and also for all positive integers, this will be divisible by 7. What does that even mean? Don't worry, I will tell you. So, 3 to the 2 times n. When n is equal to 1, we'll have 3 to the power of 2 times 1 plus 1. Plus 2 times, again, n is equal to 1. This is 2 times 2 to the power of 1 minus 1. We're just substituting n into this expression and showing what happens to it. And if this is divisible by 7, that means that it's going to be a integer multiple of 7. So it could be 7, 14, 21, 28, 35, 42. What's another multiple of 7? 7,000, 7,777. Any multiple of 7 that you like. As long as it, and we'll see here, the thing that all these terms have in common is that they are 7 times an integer. This is important, I'm going to come back to this later. But anyway, so, like I showed you, when you substitute n equals 1 into this expression to find the very first one of these numbers, then we'll have 3 to the power of 2 times 1 plus 1 plus 2 to the power of 1 minus 1. So this is going to be 3 to the power of 2 plus 1 is 3, so 3 to the power of 3 plus 2 to the power of 1 minus 1 is 0, 2 to the power of 0. So this is 27 plus 2 to the power of 0 is 1, which is 28. We actually looked at this before. This is one of the examples that we chose. It's 28. That's a multiple of 7. Is this 7 times an integer? You bet it is. This is 7 times 4. Therefore, divisible by 7. Therefore, true for n is equal to 1. Okay, our statement's true for the base case. But how are we going to show that it's true for all the other integers? I hear you cry. Well, we use the same method, essentially, as we did in the first question. Assume that it's true for the general term n is equal to k. As I outlined before, we're just going to substitute k into this expression. This is a completely general term. 3 to the 2k plus 1 plus 2 to the k minus 1. This is a bit different. What is this going to be equal to? Or is this equal to anything? As we said before, this is equal to 7 times an integer. How are we going to say that? We know this is going to be, or we're assuming that this is divisible by 7, which means we're assuming that this is 7 times an integer. The way we're going to say that, we'll say this is equal to 7 times p. And this will work if p is an integer. If this is equal to 7 times some p, we don't really care what the p is, we just need to care that it's an integer. Then that means this is going to be divisible by 7. Very cool. Prove true using the assumption for n equals k plus 1, for that very next integer, immediately preceding n equals k. Okay, what are we going to have? We'll substitute k plus 1 everywhere we see an n. So we'll have, what is this? 3 to the power of 2k plus 1 plus 2 to the power of k plus 1 minus 1. This is also going to be divisible by 7, or we're going to prove that this is also divisible by 7 using our assumption. And we're going to do that in a similar way. We'll say it's equal to 7 times sum q, again where q is an integer. So if this is divisible by 7, then it will be 7 times sum q. And we're going to show using the assumption that this is equal to 7 times some integer q. Alright, so we'll start in the obvious place. We're just going to expand this. 2k plus 2 plus 1. 2 plus 1 is 3, so this is 3 to the power of 2k plus 3 plus 2 to the power of k plus 1 minus 1, which is just k. I'm going to say this is our left-hand side, so I don't have to keep writing it. And plus, we're just trying to show that the left-hand side is equal to 7 times sum q. So our left-hand side is equal to this. Alright. Can we do much more with that? I don't really think we can. But what we're going to do, remember, we have to work our assumption into this somehow. Okay. The easiest way I can think of is to directly substitute, because we can see it's pretty similar. We're going to directly substitute what 2 to the power of k is equal to, or what we've assumed that it's equal to. So we'll do this by subtracting 3 to the 2k plus 1 from both sides. 2 to the k minus 1 equals 7p minus 3 to the 2k plus 1. Cool. But that's 2 to the k plus 1. We want 2 to the power of k. Well, what can we do with that? I hear you cry. 2 to the k minus 1 is nothing but 2k divided by 2. This is 2 to the 1. You use that index laws, and that's 2 to the k minus 1. And what we're trying to find is something in terms of, I don't know if you can see here, something that we can substitute as 2 to the k, but what we have is 2 to the k minus 1. All we should need to do is multiply by 2, and we'll have 2 to the k equals, well, 2 to the k. So, that might not make much sense, but I'm just going to show you here in practice, and it should make sense. We can multiply both sides by 2. The left-hand side will become 2 to the k, and the right-hand side will become 14p minus 2 times 3 to the 2k plus 1. Okay, all that's changed is I've multiplied both sides by 2. And now we can substitute directly what 2 to the k is into here. So here we have 3 to the 2k plus 3 plus what we've assumed is true. Remember? We might have rearranged it a little bit, but it's still exactly what we assumed to be true. And this is our left-hand side. So equals. That's it. Using our substitution. But now we've got some things in terms of 3 to the 2k. And we can use our index laws to rewrite that. So this is actually 3 to the 2 times 3 to the 2k plus 1. Because you would add and it would become 2k plus 3. And this is 14p minus 2 times 3 to the 2k plus 1. And this is nothing but 9 times 3 to the 2k plus 1. I'll bring this term over, which is minus 2 times 3 to the 2k plus 1 plus 14p. Oh yes, it is all coming together. Okay, 9 minus 2, we're collecting like terms, is 7. This is 7 times 3 to the 2k plus 1 plus 14p. 14 is 7 times 2, so I can say this is 7 times 3 to the 2k plus 1 plus 2p. Now something very interesting has just happened here. Using our assumption that the expression is divisible by 7 for k, we have for k plus 1, for that very next integer, the expression is equal to 7 times 3 to the 2k plus 1 plus 2p. It's obviously inherent that k is an integer, because that's what we're doing, but I'm just going to state that specifically here, k is an integer. Because what that means is that 2k is an integer. 2k plus 1 is an integer. This is going to be 3 raised to, even though k is also a positive integer. So 3 to the power of a positive integer is also going to be a positive integer. Plus 2p. P is defined as an integer. So we have a positive integer plus a positive integer is another positive integer, and then we're multiplying it by 7. And that's exactly what we have on the right hand side. I mean, maybe not exactly, but we have a positive integer multiplied by 7, and we have a positive integer multiplied by 7. So this is equal to, since this is a positive integer, and this whole thing will be divisible by 7, this means the expression is equal to 7q for where q is an integer. Which means our expression is divisible by 7. Which is really exciting, because we've shown that if we have some number k, where the expression is divisible by 7, then we'll have some number directly after that, k plus 1, where the expression is also divisible by 7. Which is very cool. So we're going to make use of this whiteboard, just once more, just to make it really clear to you what's going on here. I'm going to rub out all this stuff. If we have some number k, which we do, we have k is equal to 1. So it's true, let's say the expression okay, is equal to 1, let's call it x for 1. This is divisible by 7. And we've shown that if the expression of k, so if the expression is divisible by 7 when for some k, then it must be divisible by 7. This is our assumption. This is what we proved using the assumption. And this was our base case. So if it's true for some number, then it must be true for the next number. If it's true for 1, which we've shown, then it must be true for 2, must be true for 3, must be true for 4, and it must be true for all n positive integers. For all positive integers n, it's true. This is absolute craziness.